Howdy, y'all. My name is Brent Swidler. I'm the Director of Customer Success at SparkCognition, and this is Ben Wilson, my partner.
I'm his partner. Glad you all are here. You know, when people see people like us, right, they know we're from Texas, and usually what they're thinking about in their head is usually this. They think this is what goes on in Texas, but I don't really think it does.
Yeah.
And what's really interesting about this is we were told by the Google press people that might be offensive to cowboys, but we didn't find it that offensive.
But what really happens in Texas, what you actually think about Texas, maybe some Texas barbecue, Willie Nelson, South by South music, but South by Southwest. But what we really think of Texas is big houses and no state income tax. So, so what Ben and I are here to talk to you guys today about, we're going to talk about GCP and SparkCognition. I'm going to do a little bit of an intro into who we are in SparkCognition, and then we're going to walk through an oil and gas customer use case. Again, my name is Brent. I'm the Director of Customer Success at SparkCognition. You can think of that as a quasi-product manager / engagement manager role. My background is in oil and gas. I spent a number of years at Schlumberger, both as a consultant and an engineer. So for those of you who haven't heard about us, SparkCognition, we're an AI machine learning software provider. We have 3 main products in this space. The first one, which I'll be heavily focusing on today, is a product we call Darwin, which is for automated machine learning. We have a second product called SparkPredict, which is a software that allows users to interact with the outputs of models. So for an oil and gas customer, you can think of being able to interpret the output of a model and make decisions based on the statistics of the data sets that are coming in. And the third product is a natural language processing product that we have to help users or help industrial companies sort of make sense of maintenance logs as well as some other like NLP applications that they might have. We've been working on delivering solutions to markets in 2014, and we're based in Austin, Texas, as you could probably tell. We raised $56 million in our Series B. That was earlier this year from the likes of Boeing's Horizon X investment group, Invenergy's Future Fund. Invenergy is a large wind provider, as well as Verizon Ventures. And we list a number of companies, not just oil and gas focused. We're in government, we have financial applications, aviation, utilities, and manufacturing. And we've been highly ranked on some disruptors lists. So the idea of what we're going through today is a product that we have called Darwin, and I'm going to go into a lot more details about what Darwin actually is, but it's a automated machine learning tool, and it differentiates itself in many different ways, but as of right now, Darwin sits on Google Cloud, and you can access Darwin on Google Cloud. It's a user makes a call to Darwin's API, which they can upload data to Google Storage, and it uses Google Compute to actually do a lot of the machine learning work that's happening behind the scenes. And I'll go into a lot more detail about how it actually works, and it'll get a little bit technical, so look forward to that.
Awesome. You didn't press the button. There we
There you
go.
go.
So we're here to talk about how machine learning works in the oil and gas industry. For me, one of the things I like to think about when I think about machine learning is what platform are you going to build upon? When I think about a platform, I think about it in basically 3 main ways. The first, because many people around the world rely on Google Gmail, Maps, and of course the all-important cat videos. Google has created a rock-solid infrastructure that you can rely on. So if you are going to go build a petabyte-size scale seismic data lake, or you're going to do seismic interpretation, this is a performant environment that you can work upon. The second I'd like to talk about is our serverless data platform. Here we've built a unique platform that allows you to spend more time analyzing your data and understanding your data, and less time carrying and feeding your production applications or your seismic applications. So you're allowed to go down deep into your data and be able to really make decisions. Third, because we believe deeply in the power of developers, we have a developer-centric platform. And what we like to do is we like to let developers do what they love most, and that's code. While we manage the deploying, the scaling of that code so that they don't have to. Oops, I forgot to press that button. There we go. Let developers just code. This platform is actually in 5 regions, or in 15 regions right now, expanding to 15 or 5 more. These data centers are all over the world and probably within reach. And these data centers do things that are absolutely fantastic, and they have technology that just is unsurpassed. To give you a little taste of that, when you think about bandwidth, and you think about bisectional bandwidth, the entire internet has a bisectional bandwidth of roughly 200 terabits a second. Now, that sounds like a lot, but when you take a peek inside a Google data center, and we have 1,300 terabits a second for bisectional bandwidth, we feel pretty confident that we can handle almost any network-intensive application that you might have. Things like seismic interpretation as just yet an example. Now, I put this slide up, and this is always an interesting one, especially when I show it to an energy group, because they look at it, it's like, wow, that's a lot of dots, that's a lot of lines. Like, okay, you have a nice network. Why is this important? Well, we operate the largest backbone network in the world. Third parties estimate roughly 25% of all internet traffic travels across Google's network on any given day. We have more than 100 points of presence across 33 locations, 33 countries, and continue to be scaling regions and zones every day to meet customers' preferences and policy requirements. Now, I said we have a large network. The question is, when you look at that, how big is that? That's roughly 100,000 miles of fiber optic network. That is huge. Now, we'd like to think we have the largest, but we can't actually prove it because our competitors don't actually publish that information. But one thing that we all do publish are cache nodes. And we have roughly 800 cache nodes throughout the whole world, and those little gray boxes there, or gray circles there. We like to think that Google's well-provisioned, highly reliable global network matters to customers who care about privacy and security. And that's almost every single customer. One of the reasons we're able to go do this is because we do something that's called cold potato. Now, you might ask, what is cold potato? Cold potato is this. Basically, it means that what Google does is we hold on to a data packet as long as possible before it gets to the end user. And we do that because we want to provide security and privacy, but we also want to make sure it's very performant. When you look at other cloud providers, generally what they do is they play hot potato. They get your packet and they want to pass it off to an ISP as soon as possible. And it might be an ISP that might have the reliability, the privacy or quality of service that you might get inside Google Cloud. I actually think highly performant networks are really, really important. If you go talk to Niantic as an example, that make a Pokemon Go, one of the things that they did is they looked at Google's network and said, hey, that's a great network for our application, for our game. And it turned out to be the fastest growing game in the internet, and they had to have a network like ours to make it work. But the question you have to ask yourself is, if you're in the energy business, why does this really matter, right? I'm not making games. I'm actually going and looking for oil and gas, or I'm producing electricity. Since most oil and gas companies or energy companies are all over the world, they need secure communications in places like Africa, Western Australia, all over Asia, Alaska. We have a network there. We have edge nodes and POPs everywhere. So you can make sure that your data is going to get there performantly and also securely. Now, when I talk about the platform, I'm really enamored with it because I'm a developer and I like to do these things. The question is, what are others thinking, right? In this case, this is Forrester, and this is their wave chart, and they happen to put us in the leaders circle. I like that. I think it's true. But I like to think it's more because we have integrated new things together, like languages like Go, Kubernetes container clusters, globally scalable databases like Spanner. And we've also got that global network all over the world with more regions coming on that allows you to have the best experience that's highly reliable and secure. Now, for me, one of the reasons I like SparkCognition is I like to think that's one of the reasons why they decided to build on Google Cloud Platform. So with that, let me hand it over, and you can go on.
Thanks.
Sure.
Yeah, so as Ben mentioned, a lot of why we chose GCP was because it was driven by our engineers. So in that case, we decided to put Darwin, which is our automated machine learning product, onto Google Cloud. So what is Darwin, and what is it in the context of the industrial space, and especially in oil and gas? So I'm going to go through a little bit about how it works and what's happening behind the scenes, and then we'll get into an oil and gas use case. So for those of you who aren't aware of the issues with industrial data sets, we're essentially working on sensor information coming off of big machines. And sensors are really inconsistent and untrustworthy. There's sparse labels, so people are not sitting there labeling all of the information that comes off of it, which is mostly required for adequate machine learning. And it's not prepped for adequate data science. Right? So if we look at two separate wind turbines, I go through the wind turbine example because it's a lot easier for people to understand relative to oil and gas examples. But essentially, if you have wind turbines in two separate locations, those are going to require two separate machine learning models. A wind turbine in location A might have a different failure profile or predictive profile than one in location B. An operator that runs a wind farm might operate their farm differently than another one. The sensor packages that are on a wind turbine will be different. And the actual turbine that's actually running in the wind farm, those will be different between two separate locations. So what does that mean? That actually means that you cannot build one model that will run on both of these. There needs to be a scalable solution, an automated solution that can build specific models for each individual asset. So when we looked at this problem, when we started out and we started receiving a lot of information from industrial companies looking for data science work, we ended up having too many customer requests for the existing data that we had. So these were some of the internal factors that we were looking at to need to build an automated solution. In addition, to actually build a model for each individual turbine, that's a time-intensive process. The current solutions that we're offering were not scalable, and there was clearly a lack of an automated solution on the market that actually could do predictions for each individual asset. Some of the external factors that point us to automation, I went through a lot of these, but there's a lot of variation from different assets depending on location, what's on the assets, and all that kind of stuff. In addition, you needed something to solve problems with sparse data and noisy data as well. So when we saw all of these problems, we went through and we said, OK, let's look at the workflow of a data scientist and figure out what we can automate around. So for a data scientist, the first thing that you do is you go through a data cleaning step, right? You take your data, you do any sort of imputation or any sort of methods to sort of make it into a functional data set. Then you go through your feature engineering practice, and you try to figure out what features you need to engineer, what you can drop, and all of those sorts of little nuances that's sort of the magic of one specific data scientist. And then you need to build a model. And if that model doesn't work, depending on what tools you use, you go back and you revisit your cleaning methods, you go back and you revisit your feature engineering methods, and you go back and you revisit your model, and it's inherently just an iterative process that can take a very long time. Now, on two separate wind turbines, maybe you can expedite this by just having a background knowledge of what usually works, but in essence, it's not going to be, you'll need a person or a data science team to actually build a model for each individual asset. So all of this requires a high amount of technical expertise, a lot of time, and there was a lack of productization tools out there that could solve all these problems. So we went out and we tried to build something that could automate the data cleaning process, automate the feature engineering process, and especially automate the model building process. So I'm going to take a quick technical segue to talk about how we went through this, and I hope that everyone can stick with me on this. So when we talk about automating the feature engineering process and cleaning step, I'll get to that in a second. But our approach towards model building, this is an image of a neural network. There are 3 layers inside of this neural network, and each circle is essentially math happening at each circle, and each line, you can think about that as like a coefficient that happens at each line. Now, what a data scientist did is they designed what this looks like. So where all those circles are and where all those lines are, a data scientist said, this is the structure of the network that I want. And what machine learning does is it goes and just tries to figure out what weights or what coefficients happen at each one of those lines. Now, if this is not the optimal network structure, there's no way to determine what actually might be. It's just that you're leveraged to whatever data scientist is inherent knowledge or whatever's in a library that already exists. So what we did was, how can we automate the search for the right network topology, or what structure actually works best for a specific data set? So we went through and we built a product that leverages neuroevolution. So it uses evolutionary algorithms to actually search for the network architecture that solves this problem. And it not only searches for the network architecture, it chooses different imputation methods for cleaning. It chooses different features after features are generated automatically. And it searches for the network optimization architecture that is perfect for or optimized for the actual data set that it's being trained on. So how does it do this? So you upload your data set, and in the first generation, you build 70 different neural networks. And we also combined it with some tree-based algorithms. And in that generation, we look at what are the genomes of those specific models that worked the best to make those models accurate. Those genomes then get mutated into the next generation and spawn 70 new neural networks off of that initial population. and we go through that process again. We take the genomes from the best performing models, we mutate and breed them into the next generation, and we spawn off 70 new models again. And that happens for n number of generations. So in this case, now you can upload your data set, and it will do all of the feature engineering, the data cleaning process, and the network search, the network architecture search, specific to the data set that you uploaded to. And this is really important when we talk about things like wind turbine A versus wind turbine B. You're actually doing a lot of the steps specific to the asset that it's being trained upon. So what do these networks end up looking like? So here's 3 separate use cases. It's essentially use case agnostic. The one on the left predicts bearing failure. That's the architecture that was trained off of 400 generations. The one in the middle, we trained to essentially mimic one of our in-house pilots using a flight simulator to try and determine exactly how his flight path works. And the one on the right that I've kind of blacked out here trades Dow futures. So when you talk about deep learning, you can see how big a model can actually get by just doing this generative process and running it for however many generations you see fit. So again, it's use case agnostic. It's not necessarily specific to industrial applications, although that's where our DNA is. We've kind of grown up in the industrial space, working on wind turbines and oil and gas assets. But with that, I'm going to kind of go through what the oil and gas application is that we've used this for. So for those of you who are not familiar with the oil industry, there's a concept called artificial lift. So when you first produce from an oil well, the natural pressures of the well will lift fluids to the surface. So if you've ever seen those images of oil spewing out from the top of a derrick, that's because the natural pressure of the earth is pushing that oil up. Now, after a certain amount of time, the pressure starts to subside. You produced a lot from a reservoir. You need a way to be able to lift that oil out of the ground. So the sucker rod pump on the left, there's about 1 million of these in operation around the world. What this is essentially doing is if you've ever had a cup of water with a straw in it, you put your thumb over the straw and lift up, and you see the column of fluid come up with it, it's essentially just doing that on repeat. So it's just kind of sucking all of the oil out of the ground. An electric submersible pump is essentially a pump that you've lowered into the ground, and it turns and pumps oil to surface. So at a certain point in the production of a reservoir, after the pressures subside, you can no longer produce to the surface, you start implementing all of these artificial lift systems. And with these, there are many different manufacturers. They've been in place since the early 1940s. There's a variety in every field, the same aspects of what I went through with the wind turbines. Different fields have different profiles. Different sensors are put on each piece of machine. And different operators have different tactics in order to make sure that they're optimizing these specific assets. So with this, we worked with a company that one of our partners, Apergy. Apergy is one of the biggest software providers that actually monitors a lot of these assets. So you can think about a monitoring software that's streaming information directly from these artificial lift systems into their platform, and there's all of their data kind of sits inside of their monitoring software, and production analysts and specialists look through this information and try and make determinations on what's going to fail, what's going to optimize, those sorts of things. Apergy also sits across wide-ranging applications, both in drilling for oil as well as producing it. So even though we're talking specifically about these artificial lift systems here, we're eventually going to start moving into more and more of these like really complex applications. You can go all the way up to drilling applications as well. But for this, as you see circled on the left, we're focusing on the artificial lift systems. So the way that this works in practice is that an ESP in the field will stream data directly into an Apergy software where someone can make interpretations off of what's actually happening inside of the well and make decisions. And then we'll take that data either through an API or through just like a downloaded CSV from their software and put it into Darwin, where that will build a predictive model. And Darwin sits in Google Cloud. That model can then be put back into Apergy's software, and any user, any producer can actually just make determinations off of the prediction model. Now for us, Darwin sits, we have it as a standalone software, and I'm going to go through that demo. You can upload CSVs just to the software that sits on the cloud, or you can leverage it in sort of an API call connection to to any sort of monitoring software there. Now, here I talk about this specific monitoring software, but you can imagine it being any sort of monitoring software or business intelligence tool that you want to put it into. I had an executive come to me and say, well, in the context here, what do you guys mean about BI tool? And I said, yeah, you don't even know. We're thinking so far past AI. No, that didn't hit that well?
That's a bad joke.
Yeah.
That's just a bad joke.
No one was prepped for it.
We weren't sure if it was going to be good, but now that I see it,
I thought that hit a lot harder. It's already thinking past AI. So I'll go through the demonstration of how this actually works. So I'm going to upload this data set. What this data set is all of the information that's coming off of this electric submersible pump. This is an electric submersible pump, so it's the one that you lower into the ground and it pumps oil to surface. What we're trying to do is do a prediction on how much oil it will produce within the next 7 days. So off of the sensor, we're getting some metadata on where this well is actually located, production figures, so oil, water, gas. An oil well doesn't just produce oil, it produces a mixture of oil, water, gas, and other sorts of dead dinosaur stuff. And then you also have the tubing pressure, casing pressure, and all of the sensors coming off of the pump. And again, what we're trying to get to is just a very simple prediction of what the next 7-day forecast will be. So within our software, and this is the software version, you can also set it up where it just builds models automatically through a connection. But what we're going to go through is here, I've already built all of these models. They're basically cards that sit inside the software. And when I want to create it, see if it starts playing. I go create new model. And I can upload or name the model that I want to create. In this case, it's 7-day production forecast. I can give it a description. And then I'm given all of these workflows. So infer values, forecast values, infer categories, find patterns, or predict events. So in this case, we're trying to build a library of these sorts of cards that, depending on the workflow people want, this can sort of organize the data set in that fashion. Infer values is a simple regression. Forecast values is just shifting that sort of target column to be able to predict something in the future. Infer categories, this is a classification. Find patterns is our clustering approach. And predict events is our strategy towards predicting a point in time. In this case, we're going to go ahead and we're going to infer values. So I go to this card, and I'll click infer values. You can kind of go through and see all of if you have any questions on the software, you can go through. And here I'm pointed to, I want to upload, drag and drop my data set. Give a little description of what the data set should look like. So we try and formulate everything in these rectangular formats, where if you think about this as an Excel file or CSV, all of your inputs are in rows or in columns, and every timestamp is in rows. And one of your predicted outputs is in the target column. So you go find your data set. You can visualize your data set here, and then you can go ahead and select the targeted column. So in this case, you're going to go ahead and select the column that is oil production prediction, click Next, and then you're driven to a point where you can choose how long you want to train your model for, or how long you want to go through, how many generations you actually want to go through and actually build this network architecture. Obviously, the longer you train for, the more it should converge. We're giving out metrics as well to make sure that you can see how well it's converging over time. But this, as of right now, is sort of you can just determine the amount of time that you want to wait for this to train for. There's also advanced features. You can change the accuracy targets. For this, we use normalized root mean squared error. But now we're building our model. Behind the scenes, it's going through this process of building models, determining the right genomes, mutating those into the next generation, and continually going through that process until we derive the network architecture specific to this data set. We give out the statistics on this specific model, so you can see how accurate the models got over generation or over time. You can look at all of the statistics around the data set that you've uploaded. In addition, you can eventually get to the point where you're looking at feature importances. Here's the graph of the actual output. So you can see your predicted versus actual and see how that trends over time. And then you can look at your feature importances, or here you can see in an Excel format or CSV format, the predicted versus actual. In this case, now you get to the point where you can look at what features are actually driving these predictions. So this is the model-based prediction feature importances for this specific ESP, for the model for this specific ESP. And once you have your model built, you have a number of options. Either you can run, meaning test your model on unseen data. You can publish it, or improve, meaning upload your data, upload new data to train the model further. You can publish it. That means making an API call to the model that you have, or you can download it in the pickle file format that we have, so you can put it into a runtime engine. And now we're gonna upload a test set. So uploading the test set, you can upload go in the same format as drag and drop. And you have your predictions. So here is now the predictions on the next test set. We're doing 7 days production forecasting, and now you have your model built. You can see the testing accuracy. And in addition, we actually give out another feature that gives you a per prediction feature importance. So when I click on a value, I can see what's driving this prediction down or less accurate, and what's driving this prediction to become more accurate. So on a per prediction basis, now you can see what's actually driving your predictions. So here, through this entire tool, we went through the process of uploading a data set from an ESP, building a model to predict the forecasted values of the next 7 days production, and then being able to look at the model output and test it on new data sets and see each individual prediction and what drives that up or down. So even more than that, the way that I like to think about this from the oil and gas perspective is, what decisions can I actually make off of this model that I've now built? So in this case, what I've gone and done is I've uploaded the data. I have the test set up there, and I changed some of the control parameters that I have as an operator. So in this case, I can make the pump faster, or I can make the pump slower, and I can see how that impacts my production outcome. So the gray line here is the actual changed production, where the orange line is what was originally predicted. So when I make control parameter changes to my pumps, I can see how this impacts my production figures. And now prediction becomes part of my optimization plan. So in this case, the average production increase by changing the pump parameters increased by 700 barrels per week. And now you can go ahead and just make changes and see how that might impact the optimization of your ESP. Now, for those of you who are oil and gas people, you might look at this and say, well, it's really actually kind of rare to have a production figure per well. So in actuality, what happens is you have upwards of 60 wells producing into one massive tank. And inside of that one tank is where you get your production figures. So in this case, you actually have all of these wells that are using different types of artificial lift systems, different types are operated possibly by different people in different fields, and they're all going into one battery that actually is producing, that's the only targeted outcome. So for the first one I went through, I had this 7-day production forecast. That 7-day production forecast is specific to that well. In actuality, you'll have 60 wells that are producing into that one forecast. So now your optimization is, how do I change all of these pump parameters in order to make sure that I'm driving the most production?
Yeah, I mean, for me, for those of you who've actually operated batteries and operated pumps, this is like the realistic situation. I've done a whole bunch of like AI trying to do prediction and also try to do preventative maintenance and try to be able to predict failures. And the biggest challenge is being able to go out there and say, okay, I have a battery, got 60 wells. Odds are all 60 wells were not drilled by me. They were drilled by probably 3 or 4 other parties. They have 3 or 4 different sites of equipment. They have different types of sensors. So being able to have this iterative approach to going and looking at the data that's coming off and being able to do predictions by well makes a huge difference. You can think about it from an operational perspective and how full is that tank going to be. You can also look at it just from a maintenance perspective too. So when I look at this as an operator, I look at it and say, this is really, really important. One other thing I'd say too is, in case you don't recognize the name Apergy, that used to be Dover.
Yes.
And most people recognize Dover as one of the largest artificial lift manufacturers in the world. And when you think about artificial lift, you think about those pushing them down into the well, and usually put 3 or 4 or 5 of these things together, and being able to get these things to operate correctly across a set of batteries like this, really complex. So this really does simplify that process. I will also mention is, if you didn't see the dev keynotes today, they actually did all of theirs live. They didn't use video like you did. So maybe next time we need to do it live.
Yeah, I appreciate that. Thanks, Ben.
Yeah, I'm here to help.
Yeah. I mean, the big thing here is that what we're going after is the scale of the problem that's actually at hand here, where there's upwards of 1 million of these wells in operation around the world. So being able to build these models automatically and through the tool that we've built is a huge benefit to a lot of oil and gas operators. And being able to make these changes and optimization plans in real time and see how that impacts the predicted production is going to be pretty huge. Kind of back to Darwin for a second. I know that I kind of pitched it originally as this sort of use case agnostic position, and in reality, we've tested it on a number of data sets. We've done a number of Kaggle competitions as well, where we've seen that it's actually a pretty useful tool, depending on how long you train it for or how long you want to go through the process. It really does well for time series, especially when we add sort of recurrency aspects or looking back into the past components to model building too.
In case you don't recognize, you got to go back one. I got to say something.
Yeah.
Kaggle credit card fraud. Google owns Kaggle, and nice to see that we can actually do something right there, huh?
Some of the new things that we're adding in here. Unsupervised learning, we've had some success with different approaches on unsupervised learning before. Now we start to automate and do a very similar process for a Gaussian mixture model variational autoencoder. That's a fancy speak for saying we're doing clustering and dimensionality reduction in one step. In addition, what we call normal behavior modeling, where it's trying to just predict normal or not normal and what that actually looks like. We also use a very similar approach towards leveraging the evolutionary approach for building autoencoders. In addition, we're still working on our user experience, so any sort of feedback that you have on what you'd like to see or what those cards might look like or workflows that we can sort of automate to make sure that the tool works for the design process. We're working on that as well. And then we're always working on speed and accuracy. So speed in the model development process composes of both leveraging Google and their expertise, as well as our approach towards making the evolutionary algorithm smarter. With that, I mean, it's been awesome working with Google. Ben's been fun, even though he kind of makes fun of me a lot.
My job.
Yeah.
Oh, thank you. I'm Ben Wilson. I'm the smarter, better looking cowboy. This is Brent.
Yeah.
Oh, I'm sorry. You're the better looking cowboy.
There you
We
go.
appreciate you all being here.
Yeah.
Thank you very
Thanks.
much.